Morning, everyone, and welcome to Earth Science Week. We are very excited to have everyone here today joining us. We've just got our presenter coming in from Winton in Queensland. Hello. So, I've actually got my backdrop is from Winton today, a little bit of a model from the Winton Stampede. Grant, we've just got you on mute at the moment. If you would like to unmute, we can see your beautiful background of the earth behind us there. While we're waiting, if you wanted to put into the chat where you're coming from across Australia today. What we love about our Earth Science Week programs is we have people coming from across the country, from schools and homeschools and individual organisations, and that's what we absolutely love. Oh, lots of people from Queensland, Grant.
All right. Excellent. Can you hear me now?
Yes, we can. Thank you. I'm going to hand straight over to Grant from the Australian Age of Dinosaurs for our first presentation of Earth Science Week today. And I'll join you shortly. Thank you.
All right. Yes. Thanks, Karen. And welcome, folks. My name is Grant. I'm here at the Australian Age of Dinosaurs Museum. With me this morning, we've got Tennyson, who is joining us for our lesson as well. And we'll quickly zoom in, jump onto our lesson here, and we'll have a look at where we are right here in Winton. So this little video should bring up for me. Let me just get this right. And let's play this one here. So just to zoom in on where we are in Australia, let me play. We're right here in Queensland, of course, and we can see coming out here to Western Queensland, that's our jump up, the little mesa or plateau that we are on here in our museum. And so we can see ourselves there, and it really is out in the middle of outback Australia. Some flat plains in the background. That's our black soil where we find all of our dinosaurs. But you can see behind me here some of our bronze model dinosaurs, and yeah, some of the amazing views that you can see around our museum here. But let's jump forwards a little bit and we'll have a look into the details. All right. So one of the things that we find, you can see there, is a piece of dinosaur bone here. And this is a simulation. It's a piece of real bone, but it is inside our museum on a display that shows exactly what we look for when we are finding our dinosaur bones outside in the field. And Tennyson's got a piece here, a small piece of sauropod lower limb bone, if you think something around the ankle. And we'll just put this one under the close camera here to have a closer look. We should see. So we can see there we've got the bone itself. It's just a small fragment, and it's been broken off down near the ankle. So it's just above the ankle of one of these large sauropods with that long tail, long neck, plant-eating, four-legged herbivores. And we can see the end of the bone there. Hopefully you can see some of the detail just in this region around here. We've got some of the little porous cavities in that softer bone in the middle. Whereas the end where we're going down to the ankle joint there, it's a bit more rounded and it's pressing against some cartilage and a lot more solid of that bone. So what we're about to do is to have a look at how our sauropod bones and all of our other dinosaur bones as well end up here in Winton and how they can become preserved, because this really is the geology and the earth science of what happens out here. So let's jump into one of our dig sites. This is what we typically find when we're out in the field somewhere. We see a dig pit here. We've got some dirt. We've cleared off the top layer of dirt, and most of that is our black soil. And when it's rainy and we get wet on that soil, it really becomes very, very boggy. We simply can't go out there and do any digging at that time. We have to wait until it's dried out, but then we can take, like you can see an excavator there, it lifts off the surface layer, and the Winton Formation where we're looking for our dinosaur bones is usually about 2 or so meters underneath that black soil. So we take off the top layer first, and then we have to very carefully start getting down by hand the last layer towards where those bones are. And that is a really amazing process. So let's have a look at a typical dig site. One of the things that we have to do is to map out where we find the bones in that dig site here that we can see behind us. So we start to think about, where are these bones in relation to each other? Because if we're finding pieces of, say, ankle bones or lower limbs, maybe some toes, some of the bones down in the foot, we need to know, are they related from perhaps the same animal? If they're sitting right next to each other, there's a chance that is quite possible. And if they're scattered meters apart, then maybe we don't really know exactly how closely related they are. But we like to map that out so we can get as much possible detail and try and understand exactly how these bones might be related. So one of the things we do is put on a grid. So we literally take these photographs with a drone from the air, we map the site out very accurately, and down on the ground, we put out this grid so that we know exactly what position each one of these bones was found and what it was found in relation to, because that really is a very key step. Now, the next thing, let's go and have a look at how our bones really become preserved and what this black soil is. So if we look at this photograph here, you'll see a couple of really deep cracks in the ground. And this is when the black soil is dry. So the middle of winter, it's our dry season. As this clay-rich soil starts to dry out, it shrinks. And that's what leaves all these gaps, and those large cracks open up as the soil's shrinking and shrinking as it loses the moisture. And those cracks, they can be extremely deep. Like if you dropped a phone out of your pocket down some of these cracks, they'd go down a meter or two. You're not getting it back. So it really is some very deep, large cracks. And that shrinking process is part of what helps us to find our dinosaur bones. Because the reverse process, when we get into summer, we find the wet season and all of this loose material you can see sitting on top there, the rain just washes all of that loose dust and debris straight down to the bottom of the cracks, and then it expands again. And it's got nowhere to go because there's soil everywhere to the side, so it starts pushing or lifting up. And it creates what we call this self-mulching process in our black soil. So I'll have a quick look at this video. Tries to explain it a little bit in an animation. So this lighter layer down here that we can see at the bottom, this is our Winton Formation down here. The darker layer on top is the black soil. We've got some rains coming across, washing the sediment down from the top. And very slowly, any of these larger fragments of bone that get broken off or damaged, they slowly get lifted up in these expansion and wet and dry cycles. The soil slowly lifts up and literally rotates around and brings anything from the very bottom, it starts bringing it to the top. It does take thousands of years for that to happen, of course, but that's one of the clues. Whenever we get to somewhere on our properties that you see these types of bones, these fragments, and you think, oh, is that a dinosaur bone? Usually the graziers, somebody from the museum will have a closer look. And once we found those, identified that, yep, that's a piece of bone. Usually that now becomes, we take a GPS tag and we now know where we're going to perhaps do our next dig, because hopefully there might still be some bones still preserved in that Winton Formation, just that little bit deeper. So we've got a simulation that we're going to try and show you here this morning about how this black soil process works. So what I'll do, we've got a couple of things here. I'll just bring Tennyson in here, and this will make a little bit of noise, but we might mute the microphone for a second when we make most of the noise. So what we've got here, a couple of regular marbles, and I'll just give Tennyson a couple of these smaller little plastic beads. We'll put them under the close-up camera so we can have a a closer look, and you can see exactly what we're dealing with here. So you can see we've got a couple of large marbles, some smaller regular sizes, and then those tiny little plastic colored beads. Now, Tennyson, which ones are the heaviest of
Well, the
those?
marble, they're really heavy.
So the marbles are really heavy.
Yep.
And the little plastic beads, yeah, nice.
Very.
Yeah. All right. So we'll put the marbles back in here. So we've got, if you want to hold that one for me, please.
Yep.
We've got the really heavy marbles just here in the jar. We're going to take the small, very small pieces of plastic beads, pour these ones on top. Now, with the small ones on top and the large ones on the bottom, this is going to become a demonstration, a little bit of how this black soil process works to lift our large bones all the way up to the top. So I want you to think about this one in the comments, perhaps. If you think which one of the type of fragments, the little tiny plastic beads or the very large marbles, the heavy ones, which ones do you think will actually rise to the top if we take it and give it a really, really good shake and start shaking it around for about 30 seconds or so? I want you to try and guess which ones will come to the top. While you're doing that, we're going to put ourselves on mute, shake this and make a lot of noise, and then we'll come back and show you the end result. So before we go away, we'll just put it on so you can see. We're not trying to trick you here. We really have got all of the small beads on top. Maybe there's one marble there we haven't quite covered, but we've got the small beads on top. Most of the marbles are all the way down the bottom. So we're about to give this one a good shake, or just put our mute on because it does make an awful lot of noise. And we'll give this one all right. So we can see the end result there. After that little bit of shaking, most of those marbles, the larger, heavier fragments, they've come to the surface, and the tiny little plastic beads have all sunk down to the bottom, which really is quite incredible. You can see all the tiny beads on the bottom layer there, and most of the marbles are now up on top. So it seems a little bit like we'd say counterintuitive. It goes against what we might first expect. And Tennyson described an example earlier, talking about Lego. Has anyone ever had this experience? If you tell us about your Lego experience.
So I had a big tub of Legos when I was a kid, and I'd always have to, when you're looking for the little tiny pieces, I'd always have to dig right the way down to the bottom to find them. I spend a really long time trying to dig out those little tiny pieces at the bottom of the tub. And it always happened that, you put everything together on the pile or in the bin of Lego, and all of the little ones would just find their way to the bottom, which was a little bit annoying for me as a kid. But it's that same principle of the heavier pieces, despite them being bigger and heavier, they actually float to the surface because the smaller ones find their way through the cracks between the big ones right the way down to the bottom.
Yeah, and that's a brilliant example because it's literally what happens here in this little demonstration with our marbles and plastic beads. Maybe we'll have to get some Lego and do it next time.
Yeah.
And it's also exactly what happens with the large pieces of our dinosaur bones and the tiny fragments of black soil. The black soil finds its way all the way down, fills up the cracks to the bottom, and the larger fragments slowly get pushed up to the top. It's absolutely remarkable. All right. Let's have a look next. We've got the next step, of course, is asking about what is the process that brings all of our dinosaur bones to where we find them today. And if we think back when our Winton Formation and all the dinosaurs were alive around here about 95 or so million years ago, Australia was much further south, as we can see way down the bottom here. So we're talking about down near what Victoria, modern day Victoria or Tasmania would be. And then over time, we find, if we play this little animation forwards, we'll find that Australia, the whole continent, very slowly begins moving northwards. And we'll see this, and this process, it's called tectonic plate movement. So the Earth itself is made up of all these continents that are, in fact, lighter crust material, and that tends to float on top of the denser, heavier material underneath, just like these light and large particles. And these plates or crust plates, tectonic plates, they slowly move across the Earth's surface. And so Antarctica and Australia used to be literally joined together. And Australia was way down south near the South Pole. They've split apart, and Australia starts moving northwards, like we can see in our image here. And so we find now the environment, of course, is very different today compared to what it was 95 million years ago. So that's the process that brings our dinosaurs from where they were when they were living and died 95 million years ago up to where we find them today. And there's a lot of geological erosion processes that happen in the meantime, because one of the things that we find here, remember we saw that jump up or that raised mesa layer where our museum is? We're about 70 meters above the flat black soil below us on the flat plains. And we're a much younger rock. So the rock on top of where we build all of our museum, it's only about 20, 25 million years old. It's really quite young. And there may well be dinosaur bones under our museum, but we'd have to dig down about 80 meters perhaps. So nobody's going to go and do that. It's simply too difficult. This piece of rock where we are has not eroded in that intervening 100 million or 95 million years. Whereas those black soil plains, that's where the erosion has occurred. So it's taken those soil layers and rock layers away all the way down to where we find almost to the Winton Formation. And that's what protects our bones.
Yep.
So let's have a look. Oh, hang on, it's playing the video again. Let me jump. Here we go. So here's our comparison. So we can see where we are today, where we were, or where Winton was 95 million years ago, versus where we are in that little red circle up in middle of Queensland there today.
Probably down about, that's where we
Yeah,
started.
we really have moved quite a long way north, and that changes our environment as well. So the type of trees, the plants that we find around in our environment today is very different to what it was when the dinosaurs were here. And we get some geological evidence of that, which is also pretty spectacular. So we'll have a close look up on the camera here. We've got a piece of petrified wood, first of all. So we can see there we've got the outer rough bark layer on the piece of wood there, and this is turned literally to rock, petrified wood. Now, if we turn it over, we've polished and cut this side. You'll see that beautiful timber pattern that you'd see in a nice piece of timber floorboard.
It looks just like wood.
And it's exactly around about 95 million years old. You could almost put it on your floors. It would do just as good a job. So there were very large trees around here 95 million years ago. Most of them, we believe, were conifers or pine trees, because we find a lot of evidence for that. And those trees, like modern pine trees or the large conifers, if you think of the type of conifers we find in the redwood forests, the redwood pine trees over in the United States, they're talking trees up to about 100 meters in height. So extremely large pine trees. Now, the other evidence that tells us there were lots of pine trees, we're going to have a look at some sediment that we find just on the camera here again, on the forest floor. So this is all the debris that falls down and starts to decay on the forest floor. We'll point out a couple little pieces. You'll see some tiny fragments of bark, little chips of wood, maybe tiny little twigs, some impressions that are left behind. And we also find pine cones. So let me go and I'll find a close-up. We've got a close-up image here of a pine cone for you. if we flick back over to this one, yeah, we can see that one just here. So just behind me here, we've got this magnified view of a pine cone. We can see, is there a scale? Yes. So we've got a 1 millimeter scale bar just in there. If I hop out of the way, Tennyson can point that one out for us.
Out there, and then
so that little
whole thing.
Yeah, that little pine cone, maybe it's about 10 millimeters, almost 1 centimeter.
They're tiny
in diameter. And even smaller, you can see some there in that tiny little glass vial or that we capture them. And so we have these little pine cones, all of this evidence again that tells us about what we found with our dinosaur bones. And so this is how we know the environment at the time where they were living. So it really is remarkable that we can find all of this evidence. But let's jump back again. We'll have a quick look. Right here, we've got a map of Queensland. Now I'll just jump over this side. Tennyson can probably point these out a little bit better for us. Yep. But if you can point out where Winton is, please.
Finger right. And down. Oops. There we go. Right.
So we've got Winton right there, and that's where we are today. You can see that kind of yellowish tan color. That indicates our Winton formation. So everywhere we see that color just below that kind of light or bright green, that's the Winton Formation that's about 95 million years old. And these sorts of geological maps that tell us the age of the soils and the layers, you can find these for literally your own state, any state or territory in Australia. You can find these maps, and it tells you where you might expect to find our dinosaur bones. So if you look up a geological map for your state, you should be able to find regions where there's going to be maybe some Jurassic, certainly some Cretaceous that, yeah, are the regions that you would find or people would find our dinosaur bones.
And keep in mind, this one is limited to just the dinosaurs or the reign of the dinosaurs. So you're not looking at pre-dinosaur or post-dinosaur. Anyone in any other state, this gets almost rainbow colored if you look at it when you expand it to that length. It's really interesting to look at.
Yeah, because there's so many different eras and ages, geological layers across the whole of Australia. Of course, they're talking about minerals most often, but yeah, when we're just looking at our layers that we find dinosaurs, this is a really useful map for us. And this is one of the reasons we find so many of our dinosaurs, of course, around in the Winton region. All right. So this next video, this one's going to give us some of the story of an explanation of how these bones that start out as real living dinosaur bones end up becoming rock, being processed into that fossilization, and permineralization is the word that we're going to learn about. We'll just play this little animation. So we can see here an old billabong. We've got some large sauropods wandering around. Every now and then, maybe one gets trapped in the mud and it just can't get back out again. So it dies. Large carnivores come along, scavenge on the bones, the flesh, and we've just got a few bones left behind. Some of those might get pressed deeper into the mud if an old sauropod, a few other dinosaurs wander over it. And after several thousands and thousands of years, we go to this permineralization process. We have to cover the bones, so we need water, bringing in soil and sediment. Otherwise, the bones can't be preserved. And this permineralization process, it literally replaces minerals and elements inside the bone with minerals that are in the soil around those bones that they've been covered up with. So it needs to be a wet, damp environment for this mineralization or permineralization process. So let's have a quick look at a bit more detail of one of these images. So if we look just here, you can see that little blue arrow. This is indicating some of the minerals from the soil, like represented by that little faint blue circle there, it replaces, it literally seeps in or diffuses into the bone and replaces and bonds with any of the chemical elements inside the bone, and it turns it to something else. It literally turns now to rock or stone instead of what it was once as pure bone. And the reverse process also happens. The soil sometimes takes away in that wet environment. It takes some minerals out of the bones, represented by that little grey arrow. And so some minerals leave the bone, replaced by others. And over time, millions of years, what was once a piece of bone, calcium and phosphorus, is now turned to a rock, just like the one that Tennyson is holding here in front of us.
Yeah. So all of the bone, we keep calling it bone because that's what it was. It's rock now, which is really cool. It's just replaced literally cell by cell of that bone, replaced with those minerals to turn it into a perfect replica of it, of that bone. But it's the same shape, the same everything of that bone, turned completely into stone.
Yeah, it literally, it fills up all of the cavities. Any cavities that were naturally existing in the bone get filled up and replaced with these minerals.
It even preserves the gaps in that bone, so that spongy layer. It doesn't fill those in, it replaces the structure of the bone, which is really neat.
It is absolutely amazing. And so that's the process, that permineralization of how an original once living bone in a living organism completely turns to rock or stone. And it's the same thing with like petrified wood. It really is the same process. It seeps in, the wood has to be covered, so it has to be covered in this damp, muddy sediment. And then the same thing, minerals seep into the wood. Some minerals and compounds come out of the wood and it replaces it, turns it again to rock. All right. Our next slide here, just behind us, this is a graphical or a pictorial image of a demonstration I would definitely like you guys to try at home one day, is to take a sponge, just something like this one here. You can get, you've got maybe mum or dad's got an older kitchen sponge and they're about to throw it out because they need to replace it. Grab one of these sponges, and what I want you to do is mix up some warm water and maybe a couple of teaspoons full of salt. So you make some really salty water, stir it all in, make sure it's nice and dissolved in that warm water. Put your sponge onto a nice little plate there, and then pour that salty water all over the sponge. So you get it soaked into the sponge. It's now soaking wet with this very salty water. Then you take that plate sitting there with the sponge, put it outside in the sun. If it's a nice warm day, you'll need to leave it there all day.
Yeah.
And the water starts to evaporate. And the thing that's left behind in that sponge, you can see here in the image behind us, is that crystalline layer of crusted salt that's on the outside of the sponge, but also filling all of the little pores and the holes inside that sponge. It's literally a very nice demonstration or a model of the way that our dinosaur bones actually get replaced. And what you'll find is they're a lot heavier, because this one now, once it's a piece of rock rather than bone, it's so much heavier, so many more dense, heavy minerals. And that's the process of how our bones actually turn into rock. All right. Our next image here, we just want to have a quick look at some more detail of the dinosaurs that we find around the Winton region. So Tennyson, can you just point these ones out for us?
Yep. So we have two different species of dinosaur here. There we go. Dixie, we have Matilda, and then the one just here is Oliver. Now these three are from a species called Dimantinosaurus. We find a lot of these around here. They're large, of course, long-necked, long-tailed plant-eating dinosaurs. And then your smaller one here is Banjo. He's our largest carnivore that we found out here in Winton, Australovenator wintonensis. Now he's a really interesting find for us based on the fossil that we found. But looking at the size of these things, really interesting to see how they vary. So Oliver here, oops, here we go, almost the same height at the shoulders as Banjo is. But as you scale in height, you get Matilda, who's really big, and then Dixie a little bit larger than that. So they start off as a juvenile, relatively small, but large for a carnivore, and then they just scale right the way up.
Yeah, and these are our famous favorite dinosaurs out here in Winton. We know Banjo and Matilda, our Dimortinosaurus matildae. So yeah, very large sauropods, up to 10, 15 meters long from head to tail, maybe even a little bit longer.
Yeah, we have found a slightly larger than 15-meter ones, but yeah,
So
they're
it's
huge.
yeah, absolutely large sauropods. And you can see there just for scale with a little human in the corner. Yeah, Banjo at the top of the head would certainly stand at least as tall as me if he was sort of standing more upright. But yeah, they're absolutely scary animals if they were chasing you in the dark for sure. So let's have a look here. We've got some life-size bronze sauropods, and it's really nice just to see these. Yep, I'll just get out of the way. So we can see these in our literally almost as if they would have appeared in the real environment. And we've got who's the one at the front again? The small one?
Oliver.
Yes, we've got Oliver there in the front and something the size of Matilda, like
Yep.
a more adult size sauropod there behind. And then, of course, we've got Banjo here. So Banjo, our Australovenator wintonensis, and yeah, that meter with those large teeth, lots of teeth to yeah, chew on some meat.
Yeah, and massive claws.
Yes, yes, those very large claws that are going to grab onto any prey that it's able to snap up. It's going to hold onto that. It'll never let go. All right. A little quick animation. This is approximately most of the bones that we found in Matilda. And so we can see here an animation of how Matilda might have appeared when she were walking around. So a large sauropod like this, yeah, it really is a pretty much relaxed, just walking along a nice pace. They probably wouldn't hurt us too much. Being plant eaters, of course, certainly nothing for us to worry about. But maybe something like this one is Banjo, of course, our Australovenator. You might be able to get up to some very high speeds around 20, 25.
Yeah, 20, 25 k's an hour.
Yeah, it's certainly faster than I can run.
I'm not outrunning that.
It's certainly a yeah, a pretty scary predator if that one was chasing you. So we find all of this in, of course, our Winton Formation. Now, this is a really interesting image to have a look at here. If I just step back again out of the way, we can find we've got Matilda here on the left, labeled in the, and it's color coded. Matilda is the orange bones. And that is our large sauropod. But what we found over on the right-hand side, you'll see Banjo's bones. They're the tiny fragments that in that image, they're also color-coded, but they were found together. And this is the really interesting thing. So we've got this large herbivore that has died, most probably in a billabong, got stuck in the mud perhaps. And maybe Banjo, the carnivore, was coming along just to chew on some meat afterwards and yeah, get a nice feed.
Died there too, and the bones are. This is one of my favorite photos to have a look at because it's literally all of Matilda's bones, and then in and amongst, right in the middle of it, so right around that area, is where we found Banjo. Inside of it.
Yeah.
Cool.
Absolutely incredible. So they were, it seems, somehow related. Most likely, it would possibly seem that Banjo was, yeah, scavenging on Matilda. But perhaps, you know, there was, we've seen some other explanations that maybe Banjo may well have come along while Matilda was still alive and just stuck in the mud. And perhaps, you know, Matilda can swing a tail around, break a leg. Maybe Banjo got knocked over and then also died, and they both died together. We simply don't know, but certainly it really is pretty special to find these two in the same place, the bones overlapping. It was absolutely incredible. And one of the reasons that the possible theory of Banjo having a having been injured by Matilda, like maybe he was trying to, you know, Banjo's trying to chomp away on this sauropod that's trapped in the mud. What you can see here in this image is one of Banjo's femurs. So that's the large thigh bone, the upper leg between your hip and your knee, and it's the largest bone in the body of almost every animal. And so it's in fact broken. And they can tell by looking at there in the center that it really does appear to have been broken while the animal was still alive. We can't tell 100% for certain, but there's no other scarring that would indicate that it has started to regrow.
Yep.
So it appears it may have been broken while it was still alive or very, very shortly after death. And that is one of those indicators that perhaps, yeah, there was some interaction between Banjo and Matilda before they got trapped together in the mud there. All right. We've already seen this little image. Now, what we'll do is skip ahead a little bit to, yeah, we've just got enough time for a few questions. And what I would like to point out, though, we've got two types of, I can just hold these up. We've got two types of rock here that we find typically out with our specimens in the field. So in my right hand here, this one's a little bit rough and coarse. We'll have a close look shortly under the camera. This one is our siltstone, and this is typically what we find when we find our dinosaur bones. This one in my left hand here is a sandstone, and usually that sandstone is like a coarser sand, and it does not have, when we find this type of rock, we don't find our dinosaur bones with this one. So two types of rock, they give us lots of clues about what we find in our environment. So let's have a quick close-up look here. We can see this one here is it's quite rough on the outside, but the grain size, the little individual grains, if you take a really close magnifying glass and have a look, the grains of rock in this siltstone are very, very small. Whereas in this one, we've got our sandstone, slightly larger grains, usually in size, and you see it's more of layers. You start to see more layers in sandstone. This one is the type that we don't find with our dinosaur bones, but the siltstone, this rougher looking surface, but made of finer grains, that's the one we tend to find with our dinosaur bones. So again, it's one of those clues that we often use to go and find dinosaur bones, because those rocks, they tell us whether or not we're expecting perhaps to find some dinosaur bones in that area. All right. So we've got time, I think, for a couple of quick questions. Yeah, we'll answer a few.
Certainly do. I've got some that have come in. I like the fact that great minds think alike, that we've pretty much got the same picture in our backdrop. So we had one here from Lisa linking to when you were talking about the movement of the continents. Will Australia be in the Northern Hemisphere in the future?
Oh, Northern Hemisphere, potentially. All of the continents still are moving around the surface of Earth today. It just depends, I guess. I don't know enough about the tectonic plate movements.
No.
We're running into Indonesia, so we're getting up towards the equator here, and we're moving north, I think, about 6 or 7 centimeters per year. So it's a reasonable pace that we are certainly headed further north still. But somewhere we're probably going to run into that really much bigger landmass of Asia, and that would probably stop us from going any further north.
That's what India did. Smashed right from lower or southern hemisphere and smashed right into Asia.
Yeah, and that
the
gives
Himalayas.
rise to the Himalayas, these huge mountain ranges.
Yeah.
So maybe we could potentially get into the northern hemisphere, maybe just north of the equator a little way. Yes.
Not anytime soon, though.
Annabelle was wondering, is Banjo a velociraptor?
No. So velociraptors, as part of the name, are raptors. They've got this sickle claw on their toe. So 3 toes, and the inner toe is this raptor claw. It's really spiky. As you can see here, Banjo, he doesn't have that claw. It's a Southern Hemisphere, so kind of cousin. It's a group called Megaraptors rather than True Raptors. The name's a little misleading. It's not related to true raptors. It's ironically kind of closer to tyrannosaurs, um, but it's kind of similar in the body design, which is really interesting. They seem to be both designed for pretty high speeds.
Excellent. Um, what are some of the other dinosaurs found at Winton?
Ah, we definitely find lots and lots of sauropods. That's our most common type.
Constantly.
Yes, we do find fragments of ornithopods.
Yep.
So they're two-legged plant-eating dinosaurs. Typically, the ones we find evidence of in our prints, our dinosaur trackways, they're quite small. If you think of something maybe the size of a kangaroo or an emu.
Yep.
Of course, out here, not right in the Winton Formation, but a little bit further east in Muttaburra, they found the quite a large Muttaburrasaurus, another ornithopod, plant eating. How many meters tall was that one?
Uh,
Three to
Three, I'd
four?
give it. Yeah, it's huge.
Yeah, quite a large one. We haven't found any Muttaburrasaurus yet. Maybe one day we will. That would be very nice to find. So yeah, we only find smaller fragments.
Yeah.
Yeah.
Excellent. Another question related to Banjo. Could Banjo extend its arms?
So in the diagram here, it's got them kind of like this. It can extend them forward, can sort of swing them around like this. It doesn't seem to be able to do too much of up and down, but when you've got a claw that is just like this, moves like this, moving up and down doesn't really do a whole lot. So it doesn't seem to need to. But yes, it can reach forward and lunge outwards.
Wow. Uh, there's a couple of questions about general dinosaurs, but I'm going to share some links to the Australian Age of Dinosaurs website where you can find more about the variety of dinosaurs throughout Australia. There was just one more that I thought. There was a couple of questions about Oliver, about whether you knew how Oliver died.
I actually have no idea. I think what we've got for him seems to be, say, it's a pretty good femur. So the back leg, we've got a
Yep.
bit of the front foot. I think it's just the same way as all of our other dinosaurs, in, dying in those muddy areas. Potentially it was him going in, not being too experienced with those muddy areas, got stuck, couldn't get out, and died there.
Okay, and then
Yeah.
and you're right because we don't always find enough of the bones to tell the whole story. So I always like to describe it as it's doing a puzzle in the dark with only some of the pieces. So
Yeah.
you get a bit of the story and not the whole story. Well, unfortunately, we are out of time. Thank you so much for joining us today and sharing about the amazing dinosaurs that are found up in Winton. The Australian Age of Dinosaurs Museum is a fabulous place. There's lots of great information that you can get online as well that I will share with the recording of this session later on today. So a big thank you for joining us and kicking off Earth Science Week for us today. So thank you so much and we look forward to seeing you again.
No worries. Thank you.
See ya.